Imagine a force so powerful, so utterly destructive, that it can warp space itself, devour entire stars, and yet somehow defy the very laws of physics that govern our universe. For decades, scientists have grappled with the terrifying reality of black holes, those cosmic leviathans that stand as monuments to gravitational collapse. But what if I told you that the engines powering these devourers of light might operate on principles we don't yet understand, tapping into an energy source that, by all conventional wisdom, simply shouldn't exist? To truly grasp the unsettling nature of this cosmic enigma, we first need to understand the accepted narrative of black hole power. At their core, black holes are simple, regions of space-time where gravity is so strong that nothing, not even light, can escape. They are born from the violent death of massive stars, collapsing under their own immense weight into an infinitely dense singularity. The energy we observe from them, typically in the form of incredibly bright quasars and active galactic nuclei, is generally attributed to one primary mechanism: accreting matter. As gas, dust, and even entire stars spiral into the black hole's event horizon, they form a superheated accretion disk. Friction within this disk, combined with intense magnetic fields, heats the material to millions of degrees, causing it to emit vast amounts of radiation across the electromagnetic spectrum, especially X-rays and gamma rays. This is the engine room, the conventional power source, and it's immensely efficient, converting stellar mass into pure energy with far greater prowess than nuclear fusion. We're talking about colossal energy outputs, dwarfing entire galaxies. For instance, a typical quasar can outshine 100 normal galaxies combined. But what if this isn't the whole story? What if there's a hidden mechanic, a secret lever pulling behind the curtain, generating an energy surplus that current models simply can't account for? The first cracks in this understanding began to appear with increasingly precise observations of black hole spin. Theoretical physicist Roger Penrose in the late 1960s proposed a radical idea: that a rotating black hole, known as a Kerr black hole, possesses an ergosphere, a region outside the event horizon where spacetime itself is dragged along with the black hole's rotation. Particles entering this region could, under specific circumstances, extract rotational energy from the black hole. This Penrose process was a fascinating theoretical feat, suggesting an additional energy reservoir beyond mere accretion. But even the Penrose process, while elegant, has its limits. It requires very specific conditions and isn't typically seen as the sole explanation for the most extreme energy outputs. Then came the puzzles. Data from observatories like Chandra and Hubble began to show black holes blasting out jets of plasma, moving at nearly the speed of light, extending for millions of light years. These jets weren't just powerful. In some cases, their power seemed to exceed what could be reasonably explained by the accretion disk alone, even with Penrose mechanisms at play. Early models suggested the accretion disk should create a certain amount of radiation, but the observed luminosity, particularly in certain high-energy bands, would sometimes spike far beyond predictions. It was like observing a power plant that claimed to run on coal, but was inexplicably producing energy levels consistent with a nuclear reactor. The numbers just didn't add up. Scientists were left scratching their heads, tweaking their equations, and searching for the missing piece of the cosmic puzzle. Was there some incredibly efficient process we hadn't yet theorized? Or was there something fundamentally wrong with our understanding of what powers these cosmic monstrosities? The deeper we peered into the hearts of these cosmic beasts, the more perplexing the situation became. Take, for example, the ultraluminous X-ray sources, or ULXs. These are point-like X-ray sources in other galaxies that are too luminous to be stellar mass black holes, yet not luminous enough to be the supermassive black holes found at galactic centers. They represent an in-between class, often dubbed intermediate mass black holes. But some ULXs have exhibited luminosity so extreme that they defy even the Eddington limit, the theoretical maximum luminosity an object can achieve before the outward pressure of radiation blows away infalling matter. To exceed the Eddington limit implies either a black hole far more massive than we observe, or a mechanism for energy extraction that is wildly more efficient than anything we currently understand. For instance, Observations of the ULX named M82 X-2, located in the galaxy M82, shocked astronomers. It was initially thought to be a black hole, but further analysis revealed it to be a neutron star, an incredibly dense remnant of a supernova. How could a neutron star, with a gravitational pull significantly weaker than even a small black hole, achieve such extreme luminosity, orders of magnitude beyond its theoretical maximum? It was broadcasting 10 million times the power of our sun from an object barely the size of a city. This wasn't merely pushing the boundaries of accretion theory, it was shattering it. This wasn't just more power, it was impossible power from a conventional source. The implication was profound. Either our understanding of matter falling into extreme gravity was fundamentally flawed, or there was a completely unknown energy source contributing to these phenomenal outputs. What if these objects, black holes and even neutron stars, were somehow tapping into the fabric of spacetime itself in a way we couldn't conceive? What if they were drawing energy from a fifth dimension, or perhaps from the very quantum foam of the vacuum, seemingly empty but teeming with virtual particles constantly popping into and out of existence? The idea, though speculative, began to gain traction. These objects weren't just accreting matter. They were actively extracting energy from the fundamental constituents of reality, perhaps even distorting spacetime to such an extent that they were pulling energy from a cosmic reservoir we didn't know existed. Now imagine the implications if this radical idea were true. If black holes and even some neutron stars can harness an energy source beyond the conventional accretion and spin mechanisms, it would rewrite our understanding of fundamental physics. It would imply that the universe contains an accessible, immense well of energy that we are only just beginning to perceive. Could it be related to dark energy, the mysterious force accelerating the expansion of the universe? Or perhaps it's a manifestation of quantum gravity, a bridge between the macroscopic world of Einstein's relativity and the subatomic weirdness of quantum mechanics? If black holes are, in essence, cosmic engines extracting this new energy, then what exactly is it? And more chillingly, could humanity ever hope to understand, let alone harness, such a power? The very existence of these anomalous energy outputs suggests a universe far more complex and perhaps far more terrifying than we've ever dared to imagine. It means that the cosmos isn't just a place where things happen. It's a place where the very rules are being bent, or perhaps even broken, by forces beyond our current comprehension. It opens up the possibility that other advanced civilizations, if they exist, might already be tapping into this forbidden energy, shaping their realities in ways we can't even begin to fathom. What if the most powerful objects in the universe are not just destroyers, but also the ultimate power generators, operating on a principle that could one day unlock secrets to universal power? To this day, the true nature of these engine-defying black holes remains one of the universe's most profound mysteries. While accretion and black holes spin undoubtedly play massive roles, the persistent anomalies, the objects that seemingly defy established limits, remind us that our cosmic map is far from complete. Scientists continue to scrutinize every photon, every gravitational wave ripple, searching for the definitive evidence that will either bring these enigmas back into the fold of known physics or force us to embrace a new, unsettling reality. Are we witnessing the first faint whispers of a physics yet to be discovered? A physics that could hint at dimensions beyond our perception or fundamental forces we've only ever dreamed of? The answer, like the heart of a black hole, remains shrouded in darkness. But one thing is certain: the universe is a far stranger and more energetic place than we can possibly imagine, and some of its most powerful engines are still running on a fuel we haven't even named yet. If you want more spine-tingling cosmic mysteries that challenge our understanding of reality, be sure to check out our next video, where we explore the bizarre implications of mirror matter and its potential to coexist unseen within our universe.